In this lesson, we're going to talk about the nomenclature for polyatomic ionic compounds. Polyatomic, so this is distinguished from binary ionic compounds. First, let's define what we mean by polyatomic ion. Sometimes a group of atoms carries a charge all together. We call that, as the name would suggest, poly is a root that means many, and atomic means referring to atoms. Here are some examples. Ammonium ion consists of one nitrogen and four hydrogens, all together carrying a 1 plus charge. The big blue sphere is the nitrogen, and the four smaller white spheres are the hydrogen. Nitrate ion consists of one nitrogen paired together with three oxygen atoms, all together carrying a 1 minus charge. So the blue sphere is the nitrogen and the three reds are the oxygen. Sulfate ion consists of one sulfur and four oxygens, all together carrying a 2 minus charge. So you can have different charges on polyatomic ions. The yellow sphere is the sulfur and the reds are the oxygens. Phosphate is PO4, one phosphorus and four oxygens, all together carrying a 3 minus charge. The blue in this case is the phosphorus and the reds are the oxygen. So any kind of a many atom ion is called a polyatomic ion. Now, here's the good news. The nomenclature for this is very straightforward. Suppose we want to write the formula for an ionic compound that consists of a combination of calcium ion, which is the positive ion, and nitrate ion, which is the polyatomic negative ion. Well, we would look on the periodic table and find calcium in group 2, so it carries a 2 plus charge. And you actually have to either memorize or have your teacher give you access to a list of polyatomic ions that you can look up to know the charge that nitrate is -1. There's no other way to know that. There's no way for you to guess that nitrate NO3 is a 1 minus charge other than you either memorize it or you get to look it up on a list. Because calcium ion's a 2 plus and nitrate ion is a 1 minus, it takes 2 nitrate ions to cancel out the charge of 1 calcium. Now, the way we write the formula is interesting. Because NO3 acts as one single ion, it's a group, but it's one single ion, we put that formula NO3 in parentheses, and then outside the parentheses, we put the 2 to indicate that there's 2 of them. Sometimes students get confused and they say, I see a 3 here. Does that mean there's 3 nitrate ions in this compound? No. It's only the subscript outside the parentheses that tells you how many of the ions there are. The 3 that's within the parentheses tells you how many oxygen atoms are within a single nitrate grouping. It does not tell you how many ions there are. So that's a really important and common mistake, is to confuse the 2 and the 3 and think that there's 3 ions. Now for the nomenclature, whatever the positive ion's name is, write that down. And whatever the polyatomic negative ion's name is, write that down. There's nothing else in terms of endings that you need to worry about. Like with binary ionic compounds, you needed to change the ending to "ide." Here, the name of the polyatomic ion already ends with the proper ending. So nitrate, we just leave it as nitrate. This one is calcium nitrate. You might encounter a situation where there's a transition metal, just like we did with binary ionic compounds, and you would indeed need a Roman numeral to indicate the charge on that transition metal. Let's take a look at this one. Ammonium is a positive polyatomic ion. Most polyatomic ions are negative. I'll show you a list in just a minute. But there is one very common positive polyatomic ion, and that's ammonium, consisting of one nitrogen and four hydrogens and carrying a 1 plus charge. Can you pair 2 polyatomic ions together? Sure. If one of them's positive and the other one's negative, you can absolutely pair them together. So let's write the formula for ammonium when paired with phosphate. We know that ammonium ion is a NH4 plus 1 charge, and phosphate is PO43 minus. Again, you either have to memorize it or have access to a list. There's no way to guess at that charge. Because ammonium ion is a 1 plus charge, don't think that that 4 as part of the formula NH4 means that the charge is 4. It's a plus 1 charge. If I had meant to write the formula with a 2 plus charge, I would have put that up in the superscript up high, not the 4 down low. So the up high charge is what's important. So 1 plus is paired with phosphate ion, which is a 3 minus charge. It's not a 4 minus. The 4 that you see as a subscript within that ion's formula simply tells you how many oxygens there are within a single phosphate grouping. Now, if you go back to a binary ionic compound like lithium nitride, lithium's a 1 plus, nitrogen's a 3 minus. It took 3 lithiums to cancel out the charge on 1 nitrogen ion. So just like that, if ammonium's a 1 plus and phosphate's a 3 minus, it takes 3 ammonium ions to cancel out the charge of, guess how many phosphates there are? Since we know that the formula of phosphate is PO4, and I only see 1 PO4 written here, there's only 1 phosphate ion. It might be helpful if you wish, you could put parentheses around the PO4 and put a 1 outside it, but most chemists don't do that because they know that the phosphate formula has 4 oxygens in it. This 4 outside at the end of the formula does not mean that there's 4 phosphates. The 4 is part of a single phosphate grouping. Now, here's the fun part. To name this, it's a piece of cake. The name of the positive ion, ammonium. Ask yourself, is that a transition metal? No, it's a polyatomic ion. So no Roman numeral is needed. And then the charge of the negative ion, we just write it down as it is. Phosphate, there's no change in the ending. Here are a set of steps that will be helpful to follow when you're encountering problems involving polyatomic ions. First, write the name of the positively charged atom, or if it's the ammonium ion, you would just write down the name of that ion. 2, if the positive ion is a transition metal, indicate its charge with a Roman numeral in parentheses. 3, using a list of polyatomic ions or your memory, write down the name of the polyatomic negative ion. And that's it. I would point out there's only one commonly seen positive polyatomic ion, that is ammonium. Polyatomic negative ions end with ate or ite mostly. However, there are a couple of important ones that end with IDE, which is unfortunate because students, when you see or hear hydroxide or cyanide, often students are looking on the periodic table for, well, minutes before they figure out, oh, it's not on there. Hydroxide is not a single element. It consists of both oxygen and hydrogen paired together in a single polyatomic ion. Similarly, cyanide, it's not an element on the periodic table. It's carbon paired with nitrogen in a single polyatomic ion. Here's a list of commonly seen positive and negative polyatomic ions. Do you have to memorize these? Not in my class. I give you these formulas and I end up tricking, no, I don't trick you. I just, due to the number of times that you'll use these, you're going to end up memorizing most of them. But if you want to save yourself some time and say, I'm not afraid of memorizing, go ahead, memorize these, and it'll save you time in the long run. Notice that for the most part, the names end with ates and ites all the way down, except for ammonium, that's the positive one. Hydroxide, that's OH minus. Cyanide is CN minus. And then there's one other interesting one here. HCO3 with a -1 charge is more recently termed hydrogen carbonate. All that whole thing is one word, hydrogen carbonate. It's treated as if it's one entity. It more in the past, it used to be called bicarbonate, but I guess the bi confused people. So you can use either term, and actually both of these are in common usage, hydrogen carbonate and bicarbonate. Okay, let's try some problems together. Here we're asked to write names for these formulas. We have AgC2H3O2. Now, it's going to be helpful to refer back to our list of positive and negative polyatomic ions. This chart is super helpful. I would encourage you to either write it down or have a printout of it. We actually see C2H3O2 as one of the ions in the formula we're considering. So Ag is silver. Silver is in the transition metal block, but it's one of those special elements that does not take a Roman numeral because it has a stable charge of +1 always. And then C2H3O2, you have to be familiar enough with the list of polyatomic ions to be able to recognize that and not panic when you see all those letters, and know that that is called acetate ion. So we name this silver acetate. No Roman numeral because silver does not take a Roman numeral. CD. Look on your periodic table and see if you can find CD. It stands for cadmium. And guess what? It's right next to silver. So it's in the transition metal block as well. And again, we've encountered one of those special 3 elements in the transition metal block that have stable charges, and they therefore do not take a Roman numeral. Now you might say, oh, well, how do I know what its charge is? Well, zinc and cadmium are 2+, silver is a 1+. The other ion, PO4, that's from our list of polyatomic ions, and it's called phosphate. So if we put that together, we have cadmium, no Roman numerals, phosphate. FeOH2. Now we have a transition metal that's not one of the exceptions, iron. That one is going to take a Roman numeral. So we have to think about what's the charge on the iron atom in this compound, because that will dictate what Roman numeral we write. It's paired with a polyatomic negative ion, OH. If you look on your list of polyatomic ions, OH is called hydroxide, and it carries a -1 charge. So it took 2 ions of hydroxide, which are each single negative in charge, to cancel out the positive charge on 1 atom of iron. That must mean that iron carried a 2+ or a double positive charge, and therefore its Roman numeral in the name is going to be 2. So iron, open parentheses, Roman numeral 2, hydroxide. Take a look at the next one. It's really similar to the previous one. Again, we have iron paired with hydroxide, only this time hydroxide has 3. It takes 3 hydroxide ions to cancel out the charge on 1 iron. That must mean iron's charge was 3+ this time, and so we take the Roman numeral 3, iron 3 hydroxide. Next one. Now, this looks scary, but if you have a list of polyatomic ions, it's less scary. MnO4 is called permanganate ion. So that whole bit is one entity, and it's called permanganate. The K, of course, is potassium. Potassium's a 1+ charge. Permanganates altogether is a 1- charge. So we simply name it potassium permanganate. Potassium's not a transition metal, so no Roman numeral is needed. Can we go the other way? Can we take names and write formulas? Absolutely. Our first one is magnesium carbonate. Find magnesium on your periodic table. Take a look in column 2. Carbonate. I know from the 8 ending that it's got to be one of our polyatomic ions. So look at your list or maybe consult your memory. Magnesium carbonate. Magnesium's a 2+, carbonate's a 2-. So together, 1 ion of each makes a neutral compound. So we simply write Mg and then CO3. Please note, the 3 subscript does not mean that there are 3 carbonate ions. There's actually only 1 carbonate ion, and the 3 oxygen is part of the first and only grouping of CO3. Next one, manganese 2. If you look up manganese on your periodic table, you'll see that it's a transition metal. It's element number 25. It's not one of those 3 special transition metals, zinc, cadmium, and silver, that do not carry Roman numerals. This one needs a Roman numeral. So that Roman numeral 2 tells me that the manganese charge was a 2+. Chromate. If I look on my list of polyatomic ions, I'd find chromate, CrO4, together carrying a 2- charge. So we have a positive ion that's 2+ and a negative ion that's 2-. One of each makes a neutral compound, MnCrO4. And once again, we have the situation where you see a subscript, there's the 4 as part of the formula, but that does not mean that there are 4 chromate ions. There's only 1 chromate ion. A single chromate ion has 4 oxygen atoms in it. The next 3 kind of, let's treat them all together. Ammonium sulfide, sulfate, and sulfite. Please notice the 8 and ite, sulfate and sulfite, those you'll find on your list of polyatomic ions. You'll also find the positive ammonium ion on your list of polyatomic ions. Sulfide, you're not going to find there. Sulfide is just the "ide" ending for sulfur. So ammonium paired with sulfur ion. Take a look at sulfur's position on the periodic table. It's right below oxygen. It's in column 16, which means it carries a 2- charge. Ammonium, if you're reading your list of polyatomic ions, you would know that it's a 1+ charge. So an ion that's 1+ is paired with a single sulfur atom that carries a 2- charge. Well, guess what? We need 2 ammoniums to cancel out the charge of just 1 sulfur atom in this case. So we're going to put open parentheses NH4, that's ammonium's formula, outside the parentheses 2 to indicate that we need 2 of them, and then just plain S to indicate that sulfide ion's formula is just S. Sulfate, if you look on your list of polyatomic ions, you'll see that it's SO4 with a 2- charge. Hey, it has the same charge as sulfide ion. It's just that instead of writing S, we're going to write SO4. You still need 2 ammoniums to cancel out the charge of 1 sulfate. So open parentheses, NH4, close parentheses, a 2 outside the parentheses to indicate 2 ammonium ions. And then we write the formula of just 1 single sulfate ion, SO4. The 4 subscript refers to the 4 oxygen atoms within a single sulfate ion. It does not tell you that there's 4 sulfates. Very similarly, sulfite, if you look on your list of polyatomic ions, you'll see that its formula is SO3, 2-. And when you pair that with ammonium, it's going to look really similar to the previous one. NH4 in parentheses, a 2, and then SO3, because that's sulfite's formula. Good work, students. Good luck on the homework.